Okay, so this is, we've learned about IR and NMR, and those are two spectroscopic techniques. And so mass spec is just another spectroscopic technique that gives us different information that IR and NMR don't give us. And so mass spec is generally how we get the molecular formula of a compound. So this is just taking it kind of one step further, because all the examples you've been given, they normally give you the molecular formula, and then you're using the spectra to solve the structure. So this is like going even one step further where you don't know the molecular formula, and you would use the mass spec to kind of figure that out first, and then use like IR and NMR to solve the structure. Right, so that's kind of the information you're getting here. You get, sometimes you can get tiny bits of structural information from the mass spec, but it's not as definitive as like the NMR. The NMR really puts everything together at the end. So we'll kind of go through and talk about the different pieces. And again, I'm going to be following along with your handout. So you'll want to have that out. And I'll show you stuff to look at as we go through it. So the first piece of information that we can get from a mass spec is just by looking at what's called the molecular, aka the parent ion. And so again, I'm going to leave this to you in the reading, but basically what's happening is we're shooting our molecule into the mass spec. It's going to get ionized. It's going to be shot with electron ionization, and the ions are what the detector picks up at the end, and they're sorted by mass. So it's all based on the mass of the molecule. And so normally what we do is we represent the molecular ion or the parent ion with a capital letter M, and then like a plus sign to represent that it's a cation. And then sometimes you also see it's also sometimes technically a radical. So what's happening is we're ripping a radical off the molecule, and that creates a cation. So it's what we call a radical cation. It's a very high energy thing, and it only exists in the mass spec until it hits the detector. And that's just how the detector works. So anyway, if you see M+, you don't always have to write the dot. You can just write M+. It means the same thing. You can use that interchangeably. And what the molecular ion is it's just you're taking the mass of your molecule and you're shooting it through the mass spec, and then it becomes M+. But you're only taking usually an electron off of it. It has the same mass as the parent molecule. It's just missing an electron. It has a charge now. So again, you can just say or just M+. Okay, and so M is going to be the mass of your molecule, the molecular mass. And because you're normally just detecting the mass of a single molecule, you're detecting kind of the mass of just the single whole number ratio of kind of the common isotopes of those atoms. And so usually this is, instead of, you're used to dealing with the grams per mole and stuff like that, this is going to be a whole number. And it's a whole number representing the mass of each atom of the most common isotope. So those all have whole number masses. And again, this ion, we're making this with the mass spec. So an example of what this looks like is on page 2 of your handout. So there's a mass spectrum on here, just to show you what that looks like. And so what you're going to get here is you're going to see a sequence of peaks. We'll talk about why there's multiple peaks. But there's on the bottom, this is called the mass to charge ratio, and they represent mass with lowercase m, and charge we represent with the lowercase letter z. So if you see m over z, that's just the short way of saying mass over charge ratio. Okay, and so what that means is it's essentially the mass, because you have a mass and it's divided by the charge, and the charge is just +1. So the m over z is just equal to the mass for these cases. It does get more complex. We're not going to do those complicated examples in this class where you can have things with like a charge of +2 and stuff like that, but we're not doing that in this class. We're just doing simple examples. And then here it's just the relative abundance. So it's like on a scale of 0 to 100, what's the most abundant peak? So how much hit the detector? So what peaks are hitting the detector the most? Okay, and so this one, this is representing the mass spec of methanol. So this is for methanol, and that has a methanol, and that has a formula mass of 32. Right, so the formula is CH3OH. Right, and it has a mass of 32, and so we do see that this is the mass peak here, showing up in our mass spec. But you'll see, we'll also see smaller fragments, and then you'll also see tiny, like little fragments here. So we're going to talk about what all that means. But this is our mass peak here. Okay, so I'm going to go back to just the notes. And so, again, our methanol has a mass of 32. And this is different than if I said calculate the molecular weight, right? Normally you'd go to your periodic table, you'd look up the molecular weights of these and you'd add them up and you get some sort of decimal number, right? But here we're talking about a single molecule at a time. And so it's most likely to have the mass that's made up of the most common isotopes that you would find, right? The molecular mass on the periodic table is an average of all the naturally occurring isotopes, right? So it's not a single isotope. So like for carbon, the most common isotope of carbon is carbon-12, and carbon-12 has a mass of 12, right? Because it has 6 protons, 6 neutrons. Each one has a mass of 1 AMU, right? So carbon-12 is the most common isotope for carbon, and then oxygen is 16, and then hydrogen is just 1. So if you add all those up, so we have 12 plus 4 from the hydrogens plus 16, that adds up to 32. So 32 is like the mass using the most common isotopes. Okay, so there's different peaks you'll see in the mass spec. One peak that you'll see is the one we just talked about, is the molecular ion peak. And the molecular ion peak is M. That's the one that corresponds to the mass of your molecule. And so that's the term for it, molecular ion peak. Sometimes you'll see other peaks. There's another term called the base peak. The base peak sometimes is the same peak as your molecular ion peak, but what the base peak is it's the tallest peak in your spectrum. And that's not always M, right? So if you look at the spectrum of methanol, the mass peak is not the tallest peak, right? The molecular ion peak is here, 32. There's a peak at 31 that is actually taller, right? So that happens sometimes. Okay, so just keep that in mind. Okay, so the tallest peak, it's not always M, but sometimes it is. But it has nothing to do with that. It's just the base peak is the tallest peak. It's just a term that you want to know about. It's not always M. And the base peak, it's the one that's hitting the detector with the most abundance. So it's just kind of usually the most stable thing. And we're going to get into talking about fragments because this is a very high energy process. So sometimes molecules, they fall apart in the mass spec and you get fragments of them hitting the detector. So you'll get smaller mass peaks that show up in addition to the entire mass peak because it'll fragment and then you'll get like pieces of it hitting the detector, right? So like this one at 31, right, that could represent maybe one of the H's fell off, right? And so then it's left with a mass of 31 when it hit the detector, okay? And then sometimes you'll see small peaks that are greater than the mass. So sometimes you'll see very tiny peaks, or sometimes depending on what your composition is, it might be bigger. But the small peaks that are greater than M are due to isotopes, the less common isotopes. And so we're going to talk about the isotope patterns because there's very distinct ratios of isotope patterns that will tell you what types of atoms you have in your molecule. So that's part of piecing together the molecular formula, is that you'll see these isotope patterns based on the abundance, the natural abundance of the isotopes. And that tells you kind of what atoms you might have in there. So like for carbon, for example, we're doing OChem, we're always going to see carbon. The other isotope of carbon is carbon-13. So you'll see like a little peak at M+1 that represents the molecule that has carbon-13 in it. But it's a very small amount because it's a very small ratio. So you can kind of see that in the methanol spectra. You see that little nub right here that's like at 33. And that's representing that isotope from carbon, right? So you'll see that in the spectrum. And that's not the mass of like, the common isotope. That's just representing the isotope pattern. And we'll get into that and talk about the isotope patterns right now. Okay, so next thing you look for, so you can find the mass peak. And I'm just going to kind of go through all the information, and at the end we'll put it all together and show you how to solve a molecular formula using all this information. So I'm going to go through the information, and then we'll put it all together in a problem. So isotopes is something you want to look for in the mass spec. right? Because that's going to tell you what types of atoms you have. And so this is starting to talk about isotopes starting on page 3 of your handout. So at the top of page 3 it says isotopes. We're going to go through each type of isotope information. And so it's going to kind of follow along in more detail on the handout, but I'm just going to kind of show you some things to think about just to kind of summarize. Okay, so the first peak you want to look at, and this is has to do with carbon. So the first peak we're going to talk about is the M+1 peak. And so just a little bit about the notation when we're talking about the different peaks. So the molecular ion peak, we use M+. If we're talking about everything else is always going to be labeled as relative to M. So if it's M+1, we call that peak M+1. It's just the same mass of the molecule plus 1, right? So you're just looking for that. And all of these things are cations. All the cations are being detected by the detector. And then we generally just put brackets around it. So that's just kind of how we label and refer to the different peaks, right? And so we'll get into that a little bit later as well. So this first peak, this is where you look to kind of get information about carbon. Because the ratio of carbon-12 to carbon-13, you're going to get a relative ratio of about 100 to 1.1. And so what you'll see is if you have like one carbon in your molecule, like methanol, is that you would expect to see an M+1 peak, that the abundance is 1.1% relative to however tall the mass peak is, right? So that's what you're kind of looking for. And so that ratio is just kind of talking about the number of carbons. And so normally we have a lot more than just one carbon, and so it does kind of correlate. So like for an example, if you have like 5 carbons in your molecule, so like an example would be like pentane, right? You'd expect to see a ratio where you're kind of increasing the abundance. You have more chances of getting a carbon-13 in your molecule, right? You have 5 times more chances. And so your ratio of your M plus peak to your M+1 peak, it increases. So it's no longer 100 to 1.1, it's now 100 to 5.5, right? Because you're increasing the chance that one of your molecules is going to contain a carbon-13 atom, because you've increased your chances by 5. So you increase the abundance by 5. That's getting picked up by the detector, right? So this number represents 1.1 times 5. And it's not always perfect. Sometimes due to other things that peak shows up a little bit taller or shorter. Of course, if you get other atoms in there, that can sometimes affect the height of your M+1 peak, so it's not purely just carbons. So sometimes you can use this number to calculate your number of carbons, sometimes you can't. So it's not always reliable. Okay, so just keep that in mind. But sometimes it is. It just depends on the molecule. Usually you have enough other information to figure out the number of carbons without having to calculate it. So that's just one thing that's in there. Okay, so the next peak that you would encounter, so peak B, the second peak, is the M+2 peak. So we're going 2 above what your mass peak is. Okay, and this is, so carbon-14 is very low abundance, and so you're not going to really see carbons there, but this is where you start to see heteroatom evidence. So like the ones that are most common are chlorine, bromine, and sometimes sulfur. So the most abundant chlorine isotope, and these are all in your handout, so we're on page 3 of your handout. It has all these numbers here on your handout. And so chlorine 35 is the most abundant, but the second most abundant one is chlorine 37. So it actually has a mass that's 2 greater than this one, right? It has a mass of 37. And they have a relative ratio of roughly 3 to 1. And so that's a very distinct isotope pattern because that's pretty significant, right? So if you see your mass peak and then you see a second peak that's at M+2, and they're in a ratio of 3 to 1, that's a signal that you have chlorine in your molecule, right? So just seeing that ratio, okay? And so there's an example here at the bottom of page 3. So here's a molecule that has chlorine in it, and so you can see your mass peak is here, And then you see a little M+1 peak, that's from your carbons. And then you see a M+2 peak that's roughly a third the size of your mass peak. So that pattern, seeing a peak and then a peak at M+2 that's a third the size, that's a signal that you have chlorine, right? Because if you don't have chlorine or any heteroatoms, you're not going to see anything at M+2. There's not going to be anything there, right? So if you see an M+2 peak, that's kind of a signal that you have that heteroatom. Okay, so bromine's a really distinct one as well. So bromine has a mass of 79, but then it has another common isotope with a mass of 81. So that's M+2, right? So you're gonna have, this one's almost in a perfect 1-to-1 ratio. It's not perfect, but it's close. So if you see two peaks, you see a mass peak, and then you see M+2, and you see two that are equal in size, that's a signal that you have bromine. And so again, there's an example on your worksheet right here. So that's what bromine would look like. You see an M+ peak, and then you see a second peak that's equal in size to it at M+2. And so that's kind of the pattern that tells you have a bromine, right? And then again, you see the little tiny M+1 peaks here from the chlorine, or sorry, the carbon. Okay, sulfur also has an M+2. It's not as obvious as the other two because it's just a smaller ratio, and it's roughly 20-to-1. So again, the exact numbers are on here on your worksheet, but it looks roughly like this. And so if you see that kind of pattern, that usually tells you you have one of these elements in your structure, right? Because if you don't have one of these, you're not going to see anything at M+2. There's just going to be nothing there. Okay, so we've looked at kind of how you kind of assess your carbons. You always have carbons, so it's not really telling you much if you have M+1. The M+2 peaks, these are very distinctive, so it tells you about those three atoms. The third thing that we can look for, so now we're getting on to page 4 of your handout. So these ones aren't really going to be due to isotope patterns. This is just looking for evidence of these other types of common organic atoms that are in organic molecules. And so the next peak we're looking for is to talk about iodine. Right? And so iodine doesn't really have an isotope pattern, but its major isotope is iodine 127. And that's virtually 100% of all naturally occurring iodine. Almost all of it is 127. And so what happens here is usually if you have an iodine attached to your organic molecule, iodine fragments off the molecule really, really easily. So usually when you have an iodine-containing molecule, the iodine just flies off, and you get a peak at 127 for the iodine atom itself, just by itself. So there's not a lot of other things that, it's very unlikely that you would get a large peak at 127. And so usually if you see a big peak at 127, it almost always means you have an iodine atom in your molecule. Right? So you'd have a peak at mass to charge ratio 127. Right? So this is the fragment of iodine. So as an example, I might have, like those ones we were looking at with the chlorine and bromine, you could have a molecule like this that has an iodine in it. It goes through the mass spec, and then it fragments apart, and you get stuff like this, where one of them will end up with the cation and one of them will end up with a radical, things like that, different kinds of fragmentation, that doesn't matter. The point is that you're losing this iodine fragment, and it has a mass of 127. So it usually shows up, you'll see a peak to the left of your mass peak that's at 127. The next atom that you'll have, and this is a common one in organic molecules, right, is nitrogen. And so nitrogen also doesn't have an isotope pattern because it's mostly all nitrogen 14. You're not going to see a distinctive pattern for nitrogen. And so it does have, there's this thing called the nitrogen rule, because nitrogen, because of its valence electrons, it just works out with the bonding that if your mass peak is an odd number, that means you have an odd number of nitrogens. So most of the time that means you have 1, right? But you could have 3 or 5, but usually you just have 1. That's the most common scenario, so that's usually where you want to start when you're solving your formula and see if it works out, and then maybe go back and add 3 if you really need to. Okay, and that'll come into play when we do the problem solving, right? So again, you could have like 1, 3, or whatever. It's going to be some odd number, right? If it's even, if your mass is even, that doesn't really tell you a whole lot. It means you either have 0 nitrogens or you have an even number of nitrogens. All right, and again, it's not common to, I mean, there are compounds that have multiple nitrogens, they're just not super common. So it's usually likely that you don't have a nitrogen unless nothing else fits in there. So if it's even, you either have 0 or even number of nitrogens. Right, so that'd be like 0, 2, 4, etc. Okay, so there's an example in your worksheet on page 4. Right, so this is really tiny, but this is a molecule that has 1 nitrogen in it. Right, this one has 1 nitrogen, and its mass is 121. It's an odd number. Right, and that's just the way it works out. So for organic molecules, when they have 1 nitrogen in them, they end up calculating out to an odd number mass. This one down here, here's a molecule that has 2 nitrogens, right? And it has an even mass, right, 108. So again, that doesn't tell you a whole lot. That's kind of like a scenario where you could also have 0 nitrogens. So it's a little more iffy then. The most common scenario is you have 1 nitrogen, and then that's what's happening with the odd mass. That's the most common situation. But we'll see when we solve the structures, sometimes it's a little bit of trial and error. You have to consider a couple different options and see what works out. Okay. So the last atom that's really common is oxygen, and unfortunately oxygen is one of the most common atoms in organic molecules, and it's also the most difficult one to really definitively figure out using mass spec. The good news is usually we're not just using mass spec by itself. Usually we're like taking a mass spec, taking an IR, taking an NMR, and oxygen functional groups, as you guys have seen, are very obvious in the IR. Right, like alcohols and carbonyls and stuff like that. So usually you use the IR and you're like, oh, well, I do have an oxygen, right? Because you can tell that from the IR. But oxygens don't have a distinctive isotope pattern, so they're a little difficult to find in the mass spec. They're usually assigned by kind of process of elimination. Like, I don't have any of these other heteroatoms, but I have a large amount of mass that's missing that I can't make up for with hydrogens. So maybe I have oxygens in there. Right? And you can confirm, with IR and NMR and stuff like that. So usually it's just kind of, this is a piece of the puzzle. Normally you don't just do mass spec all on its own to solve a structure. Right? So they're difficult to find. And then we're going to do some problem solving. So sometimes these are the last ones you kind of put in there. So this is what I just said out loud. I'm just writing it down. So sometimes you can assume you have oxygens if you have a lot of missing mass to account for, and you don't have other heteroatom evidence. So you're like, okay, I don't have any of those halogens, I don't have a nitrogen, I don't have iodine, I don't have sulfur, maybe, but I have a lot of mass that's not being accounted for, maybe it's an oxygen or 2, right? So that's sometimes something you can do. Another thing, we're going to talk about fragments next. If you have an alcohol, sometimes you'll see this fragment clue. So if you look at the fragments, so the lower mass peaks, alcohols have a very distinctive fragmentation that they do, and they give a peak at M-18. So if you see a peak that is 18 less than your mass, it's usually a very strong, tall peak. That indicates that you have an alcohol, which tells you that you have an oxygen. Right? And again, you can confirm that with IR pretty easily for alcohols. So what this represents, we're going to talk about fragmentation next, But what this represents, 18 is the mass of water, H2O. So 16 for the oxygen and then 2 for the 2 hydrogens. So alcohols, they do, we learned dehydration, that's one of the elimination reactions. It'll do that in the mass spec. So the alcohol will fall off as water. So this is M minus water. And that's indicative that you have an alcohol. So sometimes fragment clues can tell you stuff that's in your molecule as well. And we're going to talk about that more right now. Okay, so if you go to the next page of your handout, page 5, it goes into more detail about the fragmentation patterns. So we're on this page here, fragmentation patterns. And so what you take away from fragments is that it's just your molecules falling apart in the mass spec. And then it can give you some little hints about pieces of your molecule. But you don't want to spend a ton of time analyzing the fragments, because usually if we're structure solving, we're also putting that together with NMR, right? So you can get hints, and you can it can give you enough information to propose a possible structure, but it's not always definitive. So it's kind of you're okay, well, it could be this, but you're never really definitively getting a structure. Usually mass spec, you're definitively getting a molecular formula, and then you can sometimes hint at what that structure might be based on your molecular formula using the fragment patterns. And so there is information here. It depends on the molecule. Sometimes the fragmentation patterns are really useful. Sometimes they're not. It really just depends on the molecule. Okay, so again, if you're looking at your mass spectrum, sometimes there's larger peaks in there. Sometimes you have a base peak. Again, that's not your molecular ion. It's one of the fragments, because sometimes one of the fragments is more stable than your parent molecule. So maybe that one persisted longer, and you're mostly getting fragment in your final mass spectrum. So the largest peak, again, that's going to be your base peak, or your larger the peak. The larger the peak, the more stable your fragment is. And so also keep in mind the fragments that are being detected are cations. So we're kind of assessing cation stability here. Okay, so don't forget that the fragments are cations. They're positively charged. And so if there's a fragmentation in your molecule that leads to a stable positive charge, a stable carbocation, that's more likely to be a larger fragment piece. So for example, if you can make a tertiary carbocation, or even better, a resonance stabilized carbocation, that's likely to be a more stable fragment and more likely to show up in the mass spectrum. So more stable plus charges are more likely to show up. And again, this is a very high energy process, so you get a whole lot of peaks. And you'll oftentimes, things that aren't stable, you'll still see those because they are forming. They just might not be forming in as much of an abundance. So you'll see all kinds of weird high energy stuff hitting the detector just because it's being zapped with so much energy. And so the first major peak that you'll see alkyl fragments. And these usually have pretty distinctive masses because you're going to lose things you're going to lose methyl groups, ethyl groups, propyl groups, butyl groups, etc. And those have, their own mass. And so you're going to see the methyl groups come off, and then you'll see those fragments, and then you'll also see them as the mass peak minus the fragment, right? You'll see both. So here's a situation. This is just a figure I took from your book. This is on your handout on page 5. And so this is just giving the example of pentane and showing the different fragments it can do, right? Because every time it fragments, one side is neutral and one side is positively charged, but you get both combinations of everything. So you can get, a fragment where you've lost a methyl, and a methyl has a mass of 15 because it's a carbon, which is 12, and then 3 H's to add up to 15. So if you see a peak that is your mass minus 15, that means you lost a methyl group, right? That means you have a methyl group, right, on your molecule. Or if you see M minus 29, right, that means you lost an ethyl group. That adds up, if you added up 2 carbons, 5 hydrogens, that adds up to 29. Or a propyl group adds up to 43, or a butyl group, 57. So you get these numbers that are very distinctive for certain alkyl groups that you have in your molecule. And keep in mind, once you get to like propyl and butyl, it doesn't tell you necessarily the isomer, because you could have an isopropyl group, and that's going to have the same mass as a propyl group. Or you could have isobutyl, or tert-butyl, or sec-butyl. Those all have the same mass. So it's just telling you you have that mass, that type of group, and that's why it's not super definitive. It's just kind of like, okay, I have some sort of butyl group coming off of my molecule. Okay, so you'll see those peaks. And again, the peak, we're relating it to where it is relative to your starting mass peak, right? So that's how you would like label them. Okay, so that's kind of what's going on here. Okay, and you don't need to memorize these numbers. I mean, you can always, if you forget what they are, you can always add up to them, right? You just know that carbon is 12, hydrogen is 1, and you can figure it out if you don't want to memorize them. Again, the second one, we already kind of mentioned this one, is if you have an alcohol functional group, you'll see the alcohol fragment pattern, which I already introduced, but you'll see the M minus 18 peak, and that's very distinctive for an alcohol. So again, that's going to be M minus water. Water has a mass of 18. So if you see a peak there, it usually means you have an alcohol. And so again, they're showing that to you here. Again, I stole this from your book, where you have the alcohol. It's just doing an elimination reaction, right, to yield water. And so that's where the water goes, right? It's 18, and then you're left with a fragment that has the same mass but minus the mass of water. So that's a common fragmentation pattern for alcohols. Okay, and so sometimes, and you're going to see this also, this fragmentation happens so fast and so easily that oftentimes you don't even see the M plus peak. So sometimes with alcohols, it's really common to not even see the M plus peak. You only, like your tallest mass peak, like your highest mass peak rather, is the M minus 18. So sometimes that's confusing because it's hard to differentiate, right? Like if I wanted to differentiate between this alcohol and this alkene using mass spec, that would be very difficult, right? Because this one I'd probably see the M plus peak for this guy, and then this one's going to fragment and turn into that. So sometimes alcohols are difficult to figure out by mass spec because of that issue. But again, we have other tools for that. We have IR and things like that, NMR, that help us figure that out. Okay, so that's what's happening with the alcohol. And then the last one you'll see is when you have like things like alkenes and alkynes. Those will fragment usually in very specific places, and that's based on that carbocation stability. Because when you have an alkene or an alkyne, you now have the ability to have like an allylic cation, right, where it's very, very stable. And so they tend to fragment mostly at that position that will give you the fragment that's resonance stabilized. And so again, example in your handout, right, so if you have like this guy with an alkene, it'll prefer to fragment here, because then if you fragment here, you can put a cation here, which is then resonance stabilized, right? So that's going to be, you would expect to see a pretty big peak at M minus 43 for this molecule, because you'd be cleaving off a propyl group to make that allyl cation. So sometimes if you see that, you can start to put together little pieces of the structure. Again, it's not going to be definitive. You're not using this to kind of structure solve all by itself. But you can get hints. You can get hints of stuff by looking at the fragment patterns. Right, so that's kind of what's going on there. You're just kind of fragmenting it, and you're expecting it to fragment to give you the allylic piece. So that's like a predictable part. Of course, yeah, you'd also see the other fragments from the other pieces as well. So kind of the takeaway from this one is that you expect it to fragment to give resonance stabilized cations. Okay, so that's kind of all the information you can gather from the mass spec, at least for this class. There's more, it gets more complicated, but this is all you guys need to kind of think about. And so we have enough information, mostly just from the isotope patterns, to kind of solve a molecular formula. And so that's kind of the application of thinking about all of these things. And so the next page, page 6, is kind of outlining the different steps. This is just kind of like a sample outline of how to go through and solve the structure. I did want to point out, I accidentally put a little typo here. It says here in step 3, it's saying you can figure it out in step X. That should say in method 2 below. I think I wrote step X as a placeholder because I hadn't labeled it yet and I didn't know what it was going to be called. So this step X is referring to this down here. Okay, so I'm going to use those steps. I'm not going to read them at you. I'm going to kind of walk you through them as we do a sample problem. And so those are on the next page. So on page 7 and 8, we have the sample problems. And so we'll kind of walk through this and what's going on here. Okay, so here's a sample problem. And so I already added some arrows because I just want to show you sometimes you'll see these mass spec and sometimes the numbers will be written next to the peaks. And what's happening here is like you'll see here there's like 2 peaks, so it's like, well, which one is it labeling? It's always labeling the tallest one that's farthest to the left, right? It's just saying that's the mass of that one, and then anything else is just an isotope pattern. So it's labeling like the main peak, and then everything else that's with it is just part of the isotope pattern. So it's labeling the one on the left of the cluster of peaks. So like with the arrow, I'm showing you which peak the number goes with. But even if I didn't tell you, that's what's implied when you see the labels like this. Okay. So like for this one, where we would want to start is we're looking at trying to find, one, the mass peak. And so usually the mass peak, and this is step 1 in your solving steps, is that you're looking for the highest mass, right? And you're looking for the main, like the mass peak of the highest mass cluster, right? Because everything that's to the left is going to be a fragment. So you're looking for the highest one. And so for this one, the mass peak is that 198, right? It's not necessarily the highest mass one in that cluster. It's usually the tallest one, or in this case, you know, the one on the left. This one has a pretty distinct isotope pattern that, you know, gives you 2 tall peaks, right? And so, you know, based on what we talked about, you might already know what that is. But this one, the mass peak, or the molecular ion peak, aka M+, in this one, that's 198. And so that's important because that's going to be the mass of our whole molecule. So that's how we're going to eventually help figure out our molecular formula, because we're going to be subtracting from that as we get pieces that we know that are in there and seeing what's left over. Right? In this spectra, that's different than the base peak. So you can see here it's also asking you to propose a structure for the base peak fragment. So remember, the base peak is the tallest peak. It's not necessarily the same as M. So in this case, 169 is the base peak. So we'll come back to that and talk about proposing structures for the fragments. Okay, so in the second step of structure solving is you're asking yourself, is the mass an odd number? And the answer is no. So that's answering the nitrogen rule, right? So you're looking, is there a nitrogen, yes or no? That's an easy one to spot. And so it's not odd, so there's probably not a nitrogen, but keep in mind there's always the possibility there could be an even number, right? There could be like 2 or 4 or whatever. But most of the time it's probably 0. All right, but we can always bring in nitrogens later if there's like a lot of missing mass and nothing else is working out. So we could try 2 later once we start putting the pieces together if we need to. But usually it's 0, probably 0 nitrogens. Right, so that's the nitrogen evidence. So we can also then, look at M plus 1. This is step 3 in that series of steps. And these problems that you have right here, they're not giving you enough data to effectively calculate the carbons. You're going to see in the practice worksheet I give you guys when we're done with this, there are some examples that walk you through calculating the number of carbons. But you don't need it to solve the structure. So like here, they're not giving you that information. You would have to know the exact number of the tallness, like the relative intensity of the mass peak and the M plus 1 peak. You would have to have the exact number. You can't just estimate. You won't be able to calculate it that exactly. So here, there's no calculation data given. So we're not going to calculate the number of carbons. We're just going to estimate at the end once we figure out all of our heteroatoms. And so that's what I'm talking about here when I'm talking about the 2 different methods for putting it all together. So method 1 is like you have an exact number of carbons you've calculated. Method 2 is you don't have the data to calculate the carbons. Okay, so that's what we're going to be going to method 2 after we go through the first 6 steps. All right, and so we also want to analyze M plus 2 because we can see some distinctive stuff there. So when we're looking at M plus 2, we're looking for bromine, chlorine, or sulfur. And so again, that's based on the ratio. And so here you can see you have your mass peak at 198, you have your little tiny, M plus 1, and then you have M plus 2, which is roughly equal in height to your M plus 1, right? So we have a roughly 1-to-1 ratio of M to M plus 2. So what does that tell you? What isotope do we have? Bromine, right? That's like a signature bromine. So you don't even have to calculate anything. It's just like, look, we have bromine. Okay, so we found something. We know we have a bromine in our molecule. All right, and then we can also look, do we have a peak at 127? No. I mean, there might be like a little dinky one, but if you have iodine, it'll be a big major peak. You'll see it. And so the answer is no. So that means no iodine. Okay, so we kind of analyzed all the information here. And so we're ready to kind of start putting the formula together. And so what we do is we start with our mass that we found. So we're going to kind of be walking through method 2 on page 6 of your worksheet. And so we're going to take our mass, which is 198. So this is step A here. And we can subtract any heteroatoms that we know for sure that we have. So we know we have a bromine, and bromine has a mass of 79. Right, the main one. And so that comes out to something. Let me grab my calculator. So that comes out to 119. And so 119 is the remaining mass. We know we have a bromine. We're trying to figure out what else we have. We don't have any evidence for any other heteroatoms. And so oftentimes that leftover mass, and there could be oxygen still. So we're just trying to suss this out. We have to do a little bit of trial and error. The next thing you can do if you don't have that information to calculate your carbons is you can do what's called the rule of 13. And so this is in step B here. And this is just a rough rule. This is just something to try. It's not like super definitive, so you don't want to be like, I did the rule of 13 and I definitely have this many carbons. It's just kind of like you're trying to figure out and narrow it down what's going on. And so what that means is you can just take your leftover mass and divide it by 13, and that'll usually round to the nearest whole number, roughly how many carbons you have. right? So we're assuming this mass right now, we're making the assumption that this leftover mass is just carbons and hydrogens, right? If there's something else in there, you'll see the mass wouldn't work out. And so what I'm going to do now is I'm going to take 119 and I'm going to divide it by 13. And so that comes out, if I round it to, it comes out to like 9.1538, etc. And so that means I might have roughly 9 carbons. Okay, so I'm going to put maybe, because you don't want to like be like, yes, I definitely have 9 carbons. You're just estimating right now. Okay, so I might have 9 carbons. And so then you kind of have to go back. Okay, well, 9 carbons. What's the mass of a carbon, the common isotope? It's 12. And so I'm trying to figure out what the mass of 9 carbons would even be. And it gives me 108. And so then what I do is I'm kind of figuring out what's going on here. So I'm taking my mass, my 119, right? And I'm subtracting the mass of my carbons. So that's my carbons. And then see what I have left. So that leaves me with a mass of 11. Okay, so I might have, so like from the beginning, we know we have a bromine. We know we might have 9 carbons, so that's like a piece of our formula. And then the leftover mass might be your number of hydrogens, right? Each hydrogen is 1. So if you have a mass of 11, then that could be 11 hydrogens. Right? So that would be another part of your formula. And so that might not be right. You have to kind of put it together and make sure that that formula makes sense. Because if you get a formula that's like C2H75, that can't be, okay? So like that means you usually have that extra mass might be oxygens and things. So you have to make sure it makes sense. And so usually a way to kind of assess if it makes sense is you just put it together and just maybe do like a DOU calculation and see if it like gives you a reasonable number, right? Because if it doesn't make sense, you'll get like a negative number or like something crazy like 40 or like something that doesn't make sense. Okay, so you know you've seen DOU numbers, they're usually somewhere between like 0 and 5. So if you get like something reasonable where you can draw a normal looking reasonable structure, then that's a good estimate for your molecular formula. So like for this one, right, if I calculate my DOU, yeah, you get 4. So this one has a DOU of 4. And that's reasonable. So that's like normally something that has an aromatic ring oftentimes, right? And so I think in this problem, where did it go? It's asking you to find the molecular formula, and so we did. We found a molecular formula that's consistent with our mass spec. Right? It gives us a reasonable DOU, so that's probably a reasonable formula. And so the next part of this problem, it's asking you to propose a possible structure. And again, we can't definitively say from this data what the structure is, but we could propose something that makes sense with our formula and our DOU, right? So again, usually DOU 4, the first thing I usually end up drawing is like an aromatic ring. Just because those are common, stuff like that. And then, you know, you can start looking for other evidence of stuff. If you want to like be really exact, you could like look for fragmentation stuff. And so you'll notice here in the data we have a really strong fragmentation peak at 169. So we could look at that one peak at 169 and figure out what that is. So that's 198 minus 169. Comes out to 29. So this peak is, if we were going to label it, that's an M minus 29 peak. And if you look back at what we talked about with fragmentation, 29 is one of those signature numbers that indicates that we lost an ethyl group. Right? So it's highly likely we at least have an ethyl group somewhere in our molecule. Right? So if we want to kind of talk about that, we need to come up with a structure and then propose a fragment that's missing an ethyl group. Right? And so if we look back at our structure, again, there's different ways to put this together. There's not one right answer here. I'm just going to propose one that's like a possible structure. Okay, this is not the only answer. So we're going to have a bromine somewhere, so I might just like stick my bromine on the ring. And then we have 3 more carbons, right? We have 9 carbons total. Oh, it got really bright. What happened there? Okay, so I might put 3 more carbons. I might propose like just a propyl group. Again, it doesn't have to be that, but this makes sense with the fragmentation also because we're observing an ethyl group falling off, which would give us a benzylic cation, right? So that would be really stable. And so this could be a possible structure of that big fragment peak. That would be a nice stable fragment peak because it would have a cation here, right? And that's not definitively the structure, but that's just a possible structure that would be consistent with what we're seeing. Okay, so when I'm asking you to propose a structure for a mass spectrum, it really just needs to be consistent with the molecular formula. Okay, but if you see something really distinctive like an alcohol fragment or something like that, you should probably put an alcohol on there. Okay, the rest of the structure it's kind of iffy. Okay, but this could be a possible structure. And then answering the part B of that problem, right? What's a possible structure for that fragment? Right, this peak at 169, the one that's lost the methyl group, it could be, this guy, right, where we have that cation and we've lost the ethyl group. So again, there's multiple answers for this. This is not like the only answer. That's just, an answer that could go with this. Right, so our formula, we came up with C9H11Br. We proposed a structure, and we proposed a structure for the base peak. Right, it just needs to be something minus an ethyl group. I'm not looking for a super sophisticated answer, just something that is consistent. Right, because 29, that means we're missing an ethyl. Okay, so let's do another example. We'll do the one below it, just to get kind of another example of how to solve. Okay, so this one we gotta walk through kind of the same checklist of stuff just to see what we got. And so we want to find our molecular peak. This one's labeled for you. It's right here. Here's M, 134. So again, it's going to be usually the tallest peak that's farthest to the right, right in the farthest cluster. So M is 134. M is not odd, right? So again, hunting for nitrogens, probably not, because M is an even number. Again, we don't have the carbon data to calculate with this one. So M plus 1 isn't really telling us anything. And then M plus 2, we're not really seeing anything at M plus 2. So you can see, you might see like a little teeny nub, but it's not enough to definitively say we have anything there, right? You would see something more obvious if it was one of those heteroatoms, right? So there's no evidence of bromine, chlorine, or sulfur. So then we look for iodine by looking at 127, and there is not a peak at 127. So there's no evidence for iodine. Okay, so there's not really any heteroatom evidence so far. So this might just be a hydrocarbon. It might just be carbons and hydrogens. Okay, so again, we can just kind of jump right into that stuff and see how that turns out. So our mass is 134. And since we don't have any heteroatoms to subtract, we're just going to jump in and do the rule of 13 right away. Okay, so we're going to assess for carbons using the rule of 13. So we're in method 2, solving. And that's going to give us a rough estimate for how many carbons we have. Again, usually it rounds to the nearest whole number, but keep in mind it could be off by 1. So you could have like 1 more or 1 less if it doesn't work out. But usually it's pretty, if it's just carbons that you have left, it'll usually work out. So if we have 10 carbons, so 10 times 12, right? This is the mass of carbon. Right, and this is the number of carbons. So we would expect that to give us a mass of 120. And so if we subtract that from our mass and see what we have left over, so we're subtracting our carbons from our mass peak, that gives us a leftover mass of 14. And that 14 could be our hydrogens. So if that's just hydrogens, that would mean we have 14 hydrogens. And so with just that information, that gives us a formula of 10 carbons and 14 hydrogens, which would be C10H14. And that doesn't look too bad. If you calculate the DOU, what does that come out to? Is that 4 again? Yeah, it's 4 again. Yeah, so it gives us a DOU of 4, so that's reasonable. So we can go ahead and I think in this problem it's asking us again to propose a possible structure. So 1, we want to solve for the molecular formula. That's one part of your answer. 2, propose a possible structure. And then 3, it's asking us to propose possible structures for some of the fragments at 119 and 105. So just analyzing the fragments, because sometimes that can help you propose a better structure. If we look at the peaks at 119, so again, our mass is 134. So if we see a peak at 119, just to calculate that, that would be an M minus 15 peak, right? Because it's 15 less than the mass. And then the M over Z at 105 is an M minus 29. So again, those are going to be alkyl groups that have fragmented off. So again, if you don't remember the numbers, you can reference or calculate. 15 is the loss of a methyl. Minus 29 is the loss of an ethyl. So that just means we have alkyl groups on our stuff. And so again, just putting together an overall formula for this guy. If we have a DOU of 4, again, aromatic compound is likely. That's 6 carbons. We still need 4 more. So I don't know, you can just put stuff on there. We know we at least have like an ethyl group. So maybe just, I don't know, stick some ethyl groups on there. Sure. It doesn't have to be symmetric. You're just trying to come up with stuff that might exist. The fragment peak that's the tallest, the base peak, is this one at 119. If you look at the spectrum. Right, this is your base peak here. It's not asking you to label it, but that's your base peak. The tallest peak is your base peak. right? And so that might be consistent. So that's the loss of a methyl. And that would make sense with a structure like this, because if you lose a methyl, you'll have a benzylic cation. So that's a pretty stable cation. And so again, there's other possible answers for this. This is just one possible structure. It could be a lot of other things too. Yeah?
Would a sec butyl group be better?
A sec butyl group? Why? I mean, that would work also.
Because
Oh, because then you get two possible benzylic.
you can get both of those.
Yeah. I mean, that's another possibility. You don't know for sure, but that would work as well. Those would both be okay structures to propose. Because again, it is high energy, so it's like even this one, you still could get ethyl fragmenting off. You're going to get an unstable cation, but it's still going to form. So you can get all different kinds of fragmentations. So again, the point is you want something that's consistent with your formula. Okay, there's lots of different possibilities. And so like these fragments, if it's asking you for like a fragment structure, you're just looking for something like if it was this one, right? If you're losing this ethyl, 29 is an ethyl, 15 is a methyl that we're losing. You just want to draw some sort of fragment that's consistent with that. So like if this was your proposed structure, you might propose this as your fragment because it's lost in ethyl. Or this as your fragment with the lost methyl. You know, or like this one, if you lost your ethyl, right, you could get there. Or if you lost your methyl, it's more likely you lose that methyl because then you can get the benzylic one. But stuff like that. So these are just two different answers. They're both fine. You don't have to do both. You could do like this top one or this one. And there's other possible answers too. These are not the only two. You can do like really most of the isomers that would fit this. The most important part is solving the molecular formula, because that's the thing that you're kind of getting pretty definitively from this. The structure, you're just hinting at it. Okay, so going on to the last example problem, it's on the last page, on page 8. So this is an example of one where you might be combining it with IR data. Right, to give you extra hints about stuff. So this is on page 8. We're looking at this one. Right, so going through our checklist, right, we have our mass peak is here at 128. It's not asking you to label it, but it looks like we have our base peak is down here at whatever that is. We don't need to know that for this problem. And it wants us to do a molecular formula. So we go down our list. M is not odd, so we probably don't have a nitrogen. We don't have carbon calculation data, right? There's nothing distinctive at M plus 2. We don't have a big peak at 127, right? Our mass is 128, so it's unlikely that we have an iodine, because that would just be like HI. So we don't have iodine. And so it's similar, it might be a hydrocarbon. Or if you have IR data, this is what I was saying, you have some pretty strong evidence for certain functional groups that have heteroatoms. So based on your IR, what heteroatom do we have? We have oxygen. And we have some distinct pieces, you know, of the structure, right? We have a strong carbonyl peak here. And then we also have a carboxylic acid OH stretching here. So with that combo, it looks like we have a carboxylic acid. So that tells us we have 2 oxygens, right? So oftentimes for oxygens, you can hint at it, and I'll show you, like, let's pretend we didn't know the IR, how we would figure that out. But basically what would happen is we would do like 128 divided by 13 to figure out our number of carbons. And that comes out roughly to 10. And so if we have 10 carbons, 10 times 12 is 120, right? And so 128 minus 120 is 8. So we might have 8 hydrogens. And so we get a formula that's like C10H8. And we end up with a really high DOU of 7. And that's not impossible, it's just not common, right? And so this one actually works out. You could probably, I don't know, draw something with a high DOU like that, but it's just, you're gonna get like a really weird structure, right? So it's more likely that we have something else going on like oxygen. And so this might be something like you might try, okay, well, subtract an oxygen mass before you do the rule of 13 and see if that gives you a more reasonable formula. But ultimately, it's gonna be iffy because it's like, it's hard to definitively figure it out because you might be able to get a couple of different formulas that are both reasonable because you're really just guessing. You don't know that you have oxygen, you're just like guessing that maybe you probably do. So anyway, to definitively do that, you know, in the lab, in the real world, we're not just guessing. If we don't know, we take an IR and figure it out. So it's not like we're just like, oh, all I have is this mass spec, I don't know what to do. So this tells us we have 2 oxygens from our carboxylic acid, and so we can kind of figure it out from there. So anyway, we know we have 2 oxygens, so we can take our mass, subtract the mass of 2 oxygens. Oxygen is 16. So again, subtract your heteroatoms first. So we're left with 96. Right, this is from our oxygens. This is our mass. And then we can do our rule of 13 for carbons because we don't have any other heteroatom evidence. So 96 divided by 13 comes out roughly to 7. And so 7 times 12 is, I typed it wrong, it's 84. And so then we can take our leftover mass, 96, we can subtract the mass of 7 carbons. And then that comes out to 12. And then that leftover mass is probably the H's. So it looks like from this we're getting that we have 2 O's that we're assuming from the IR for a carboxylic acid. We have 7 carbons and 12 H's. So putting that all together, we get C7, H12, O2. And then if we calculate that DOU, we get, I'm not good at doing the math in my head, but DOU equals 2, which is a much more reasonable number, right? And again, with the IR evidence, we want to make sure it's consistent with the IR as well. It looks like we don't have any sp2 hydrogens, and we don't have any alkene or aromatic evidence, which is consistent with the DOU. We don't have an aromatic ring. So we know we have at least, you know, 1 DOU from the carbonyl, and then the other one is probably a ring because we don't have any evidence for any other double bonds, right? We don't have any alkene evidence, so it's probably not another double bond, but the ring can accommodate for the other DOU. And if you're unsure, I mean, go back and count, right? This should have the same formula that you just came up with. So again, there's other possible structures. That's just one possible structure, right? It could also be like a 5-membered ring or a 4-membered ring with other carbons branching off. We don't have that level of detail. You're just kind of guessing at what you might have. Okay, so that's the last example problem. So I'm going to stop it there and then pass out the practice worksheet for you guys.